So in the last video, we're looking at accumulation phase. We're going to continue to look at accumulation phase where we start out at $0 and we build up to a future value. And what we did in that last video is we figured out if we knew what our regular payment being paid in at the end of every period was, we found the amount of that future value. Well, now we're going to work the other direction. Given the future value, we're going to find the required payment. To reach that desired future value. And our formula looks very, very similar to the formula we had last time. Last time our formula was the future value was equal to the payment, regular payment, times that compound interest of an annuity or future value of an annuity factor. Well, to go the other direction, to find the payment, we divide by that future value of an annuity factor on each side. So the amount of a payment that's required is going to equal to that future value desired divided by that factor. 3 parentheses, 1 plus r divided by n, to the power of n times t minus 1, close parentheses, divided by open parentheses, r divided by n, close and close. So let's look at some examples of this. Alex wants to have $400,000 to retire in 20 years. How much should Alex put away each year? So we're going to plug it into the formula. We're going to figure out that payment. Our future value that we want is the $400,000. Divided by, we have our 3 parentheses, 1 plus our rate, R. I guess I should have told you that. Put away each year at 8.7% interest. So R is 8.087 here from the 8.7%. N, how much put away each year, so that's only once a year. So N is 1, to power N times T, so N is still 1, T is going to be 20 years, then minus 1, close, divided by, open parentheses, 0.087, divided by 1, close and close. So we'll start out with $400,000. Make sure you have the right number of zeros in there. It's very easy to hit an extra 1 or a short 0. 3 open parentheses, 1 plus 0.087 divided by 1, close parentheses, power of, open parentheses, 1 times 20, close those parentheses. Remember again, you sometimes, some calculators you have to arrow to get out of that exponent. Minus 1, close parentheses, divided by open parentheses, 0.087 divided by 1, close and close. And we get $8,085.79. Is the amount of money that Alex would have to put away every year to reach that amount in 20 years. Now, it seems like a lot of money, and it is a decent chunk of money. But if you divide by 12, that comes out to under $675 a month. So it is very doable. And many people are making close to that on a car payment if you have a very expensive SUV. Let's look at another example here. Peyton is 26 years old. Peyton's goal is to retire at age 63 with $650,000. How much should Peyton invest each month at 11.4%? So we're trying to find that desired payment again. That's equal to our future value here is $650,000. And we're dividing by 1, 2, 3 open parentheses, 1 plus 11.4 is our percent, so our rate is 0.114. Payment each month, so n is 12, divided by 12, to the power of 12 times, we need to go back 63, 26 to 63. If I subtract there, that is 37 years. So 12 times 37 minus 1, close parentheses, divided by, open up parentheses, 0.114 divided by 12, close and close. So let's punch this in. As you see there, and one of the problems with this long of a formula is you got to pay close attention, because one little key not registering will obviously throw off the whole formula. You have to re-enter the whole thing again. So I get $94.19. So less than $100 a month starting at age 26, and Peyton will get that $650,000 at age 63. Now, there's a couple of things going on here that makes this so much lower than the one above. First of all, there's 37 years involved here from 26 to 63, and the rate is 11.4%. Up here, the rate was only 8.7%, and it was only for 20 years. So that makes a big difference in the amount that money compounds. What we've been looking at here is something called an ordinary annuity. If it's not stated what type of an annuity it is, you always assume it's an ordinary annuity. And as you look at that timeline for an ordinary annuity, starting at that zero balance, building up to the future value, we had those periods along the timeline, regular periods, pretend those are equally spaced, and the payments getting made in. Well, in an ordinary annuity, the payments went in at the end of each period, which means that the very last payment is really at the end. It doesn't draw any interest because you make that last payment and the annuity is over. You've reached the future value. In the next set of videos, or in the next video, we're going to look at something called an annuity due. It's still the accumulation phase, but now in an annuity due, those payments go in at the beginning of each period, which means that the last payment goes in a full period before the end of the investment. So it sits there and it draws interest for a full period before the investment ends. So that's going to be our next video.